সমস্ত জুমেতেই কিন্তু আমাদের পুরো প্রায় 600-700 জনকে নিয়ে মিটিং হচ্ছে। জুমেতেই বেশি অ্যাপসটাকে ব্যবহার, কিন্তু ওই আধ ঘন্টা আগে লিঙ্কটা পাঠায়, তাহলে ঝামেলাটা হয় না। হ্যাঁ, আধ ঘন্টা 45 মিনিট আগে।
আমাদের স্টুডেন্টরা জয়েন করছে।
ম্যাম নাও লাইভ, ম্যাম নাও উই আর লাইভ।
Okay. So start allowing others to join, Devabrata.
Yes. I accept all. ছাত্র স্যার, আমি আপনাকে কো-হোস্ট করে দিলাম, প্রিন্সিপাল স্যার এবং ছাত্র স্যার।
ওকে।
I would request all of the participants to kindly stop the video and also mute yourselves.
Good morning, ma'am.
Okay, so we have reached 100 participants and we can start. Very good morning to all of you, and welcome you all to this webinar on titled From Cities to Glaciers. And we have among us distinguished speakers about whom you have shortly read in the flyer and the brochure that we have circulated. I am extremely sorry for the number of emails that you have received from our end. Because of some technical problems, we could not do it over Google Meet, and I have learned that yes, definitely I'm experiencing as well that Zoom is a better platform from my own experience. So without wasting much time, I would invite our principal sir, Professor Siddhartha Gupta, to deliver his inaugural speech.
Thank you, Abira. It's a great opportunity to be with everybody who belongs to the one of best subjects in the world, geography, who can change the world. Really, I appreciate your subject, your methodology, your field studies, process of field studies. Actually, I had an opportunity to share my views and opinions with you during your field visit at Sikkim. It was a very nice, visit accompanied by our beloved Professor Dr. Abir Dr. Roy and our HOD, Professor Shyamol Shatra, and others. So this is a great opportunity for sharing views on the topic from cities to glaciers. So there is a big range, huge range, I think, from cities to glacier. And once upon a time, there was a cold age when glacier were everywhere. There were glaciers. So now we have to find out climbing up in the hills only. So I am very happy to see the number of participants and number of our resource persons who will be delivering their valuable lectures during this day. And first of all, I must congratulate Professor Shyamol Shatra and Dr. Abira Dottoroi for organizing such a beautiful and helpful webinar when we are placed in a very difficult situation due to COVID-19, this pandemic situation. To overcome this situation, there is only solution is to organize these type of webinars, and these type of discussions will definitely help enhancing the knowledge skill of our beloved students. And I am seeing that we have amongst us a treasure house of distinguished resource persons from one of the best universities and training institutes from not only India, but also from abroad. First of all, we have Dr. Sourav Saha, who is a scholar initially from North Bengal University. Then he went to Jawaharlal Nehru University, Delhi, and ultimately he is in the University of Cincinnati. Secondly, we have Dr. Manish Jain. Is a very famous name in the field of media channels like YouTube. He is also an alumni of JNU, Jawaharlal Nehru University, and he worked hard for the development of sprawling city of Udaipur, Rajasthan. I had an opportunity to be there. Udaipur is a very, very beautiful and lucrative city. You should go at least once there in Rajasthan. So entire Rajasthan is a very huge. You have to take at least 2 to 3 weeks to visit. But for field visit, I think Udaipur is a very, very clean and green city amongst this desert place, Rajasthan. And he's involved in Exam Race YouTube channel, which has above 9 lakhs or 10 lakhs of subscribers, as told by Dr. Abira. And third, we have Dr. Debolina Mazumdar. She's assistant professor, Bradman University, Arizona, USA. So in the true sense, in the complete sense, it is a really international webinar. In some cases, we find that some person is there from Nepal or Bangladesh or Pakistan, I mean neighboring countries. But it is also called webinar, international webinar. But in this case particularly, I must be thankful to Abira. In spite of his so many personal problems going on in his family, as I know, as I was told by her that her father is suffering from some diseases, which is very difficult to overcome. But in spite of those difficulties, those personal problems, she is the leader. She is the actual leader who can come out of these personal, problems. So I must thankful to her. She is a genuine researcher. She is a genuine scholar, and she is guiding. She has been guiding over 1 decade, I think, to so many scholars for achieving PhD also. And we have a genuine and very scholarly students in our department. I can boast of my geography department because it has the PG also. It is due to our Professor Shatra's initiative that we could start the PG from couple of years, I think couple of years or last year?
Last year, there are 2 semesters.
Two semesters have gone, and so many good students are there. And Shamal Babu is so much benevolent. He always helps students with in terms of fiscal and physical help, both. So I don't linger my introduction very much, but I should say that on behalf of our Bankura Jila Shardamani Mahila Mahavidyapit family, and specifically on behalf of our geography family, I heartily welcome all the resource persons, all the valuable resource persons, and our participants who have come across from different parts of the country. I heard that there was some problem regarding this platform. So it is not a issue. You could manage it. And so many are coming. I can watch here. So many are coming also joining. So I hope it will be a fruitful discussion. There will be a fruitful discussions. And I must convey my gratitude and thankfulness to three of our speakers who have given much time in the midst of so many preoccupations they have for coming to our platform and sharing their valuable views and for their nice deliberations going to be taken place here. So with these few words, I thank you all again, and I must stop here. Thank you.
Thank you, sir. Without wasting much time, I would like our head of the department, Professor Shamul Shatra, to begin his welcome address. He's one of the most busiest person because he's Minister of State, and but he's there every time, even in the midnight hours. If I need any help, he's there to pick up my phone call, and he's there to help any student in any means possible. He's a big benevolent in this respect, a true academician, and I would like Shatra sir to deliver his welcome speech. Thank you, sir. Please, sir.
Okay, thank you. Good morning, all the delegates, chairperson, resource person, and the convener of this webinar on From Cities of Glaciers Glorious, arranged by the Department of Geography, Bankura Jela Shabdamoni, Mohila Mohavidyapit, Bankura, West Bengal. In this worldwide pandemic situation, we are trying utmost the normal and trump as new normal education and through exchange in happening using such type of platform, and we are very much compositing the situation. As you all know, the source of this COVID-19 is Wuhan, an urban center of Hubei province of China, which has limited its growth from city cap to worldwide. It has transmitted worldwide in a very short span of time. Mass transit, wide movement make this transmission as fast as China has a rapid rail transit and connected globally with huge number of flight of movement. Here today, I will speak some fact about the transmission of COVID-19 from Wuhan, China to rest of the world. On 26 January 2020, WHO confirmed and announced high risks of novel coronavirus as epidemic in China, and where rest of the world to be prepared from misuse the nature of sort of this virus infected type of systematic fever. On 25 January 2020, China has confirmed 2032 confirmed case along with 42 deaths by novel coronavirus. In fact, mostly refuted from Wuhan city. Hubei provinces fear China. The China government has already suspended of any travel movement by lockdown the city on 23 January 2020 and suspended all sort of traffic movement by air, train, bus, and ferry taking city closure area. But the discussion has been taken by government was too late, as by the novel coronavirus infected is already transmitted in different parts of PR China and also in the different countries of the world like South Korea, 19 January 2020, Japan, 20 January 2020, United States, 20 January 2020, Singapore, 22 January, Hong Kong, 22 January 2020, Thailand, 23 January, Australia, 24 January 2020, and Germany, 26 January 2020. Very instantly, when most the developed countries have been repeated their first case within 20 January 2020 to 10th February 2020, except Egypt, Nigeria, and Algeria. Other countries of African continent remain claim in this pandemic place. This episode is highly correlated with the Chinese Great Migration during the January, February, when near about 415 million people are moving towards PR China to celebrate their Lunar New Year. One megacity of Prevailing instantly determined as the source point of novel coronavirus, as 44 suspended cases has been reported within 3 January 2020, and out of which 11 are very critical. Within 1 week of 3 January 2020, there were 41 confirmed cases has been admitted in Wuhan City Hospital. When the 20th day of January 2020 come, the incidence of spread out in a steady way of Spring Festival and largest human migration has already been took place within PR China. From the date source, it has been found that 470 number of population has already been fly during 30 December 2019 and 22 January 2020, the day before lockdown of Wuhan city, which make a great threat of government level. Previous year, air traffic movement date also confirmed the huge migration took place during this spring festival time. Risk analysis also confirmed that higher the movement this period, and of the number of affected cases, lockdown process somehow makes to stoppage around the quantities of Wuhan city through the message of already has been took place in country as well as the world, in this world. Wuhan and several cities of Prevailing have shut down all types of inbound and outbound transportation on 23rd January 2020. According to China Global Television Network, CGTN, due to Spring Festival holiday, about 5 million population out of nearly 11 million have left out just before the lockdown around on 23rd January 2020. Wuhan city is one of the important cities in central China, having the industry, commercial and educational hub, provincial airport, and deep water for exporting moving internal migration in 2018. Nearly 2.5 million population left Wuhan city during Spring Festival time because this is further provide from big data of lab, huge amount of population flow have been even to Narayan lockdown period in this situation. As a result, many of the people who left Wuhan returned to their hometown, especially the above cities, the area described the during spring festival, a large number of floating population movement is taking its course, which is starting 2 weeks before the New Year event. The result of this transmission has been experienced by nearly 215 countries worldwide. Is how a city can sugar the transmission of rest of this world. Severely, and facilities are very high for USA, Brazil, Italy, France, UK, most of the developed countries. India is trying hard to combat this pandemic situation, but we are very much hopeful to overcome such situation. One of the most performing vacancies candidates in this one formulated by the University of Oxford. It has shows the positive result in the until the according to virus report. The conclusion of these trials are to be published today in their launch. A pre-narrated work the medical journal. Moreover, there is the report of this COVID-19 vaccine candidate may be available by September. According to report published in Press Trust of India, David Carpenter, the chairman of this area research ethics committee, which approved the Oxford trial, said nobody can put painful dated. This might to want the really by the working is the brick platform this company. The vaccine could be finally available around September, and that the sort of target they are working on. So, my dear participant, cross our fighter for September and of the safe during the time to fight back and beginning back to normal, not a new normal. Thank you everybody for this participant. Thank you our principal sir, our all resource person, and our departmental convener, Abiri madam, all these participants. Thank you very much. So thank you. Okay.
Thank you, sir, for your informative lecture. I would like to brief everyone, all of my participants who are watching on YouTube as well as on Zoom, that please listen to the lectures delivered by the resource person very carefully and attentively, because for certificate, we have devised a quiz and not just a simple feedback form, because it's a trend. Sorry to disappoint many of you. It's a trend that many of the people just simply register, log into the webinar and do not listen to it. So just for the sake of a certificate, and I want to prevent it. So maybe I'm not liked by many, but I wanted to do it. So there will be a small quiz on all the speeches that will be delivered, all the lectures that will be delivered, and one can go and revise the YouTube videos if they don't remember. But please listen to the resource persons very carefully. What they say, they're very valuable. And I have been a little biased to my own students from my department. So in case there are any questions, the students from Bengali medium, Hindi medium, and definitely English, can ask question in their own mother tongue. I don't think South Indian languages our resource person would be able to answer, but for that English is there. So Hindi, Bengali is okay. You can pose your questions in the chat room in both YouTube and the chat room in Zoom. And another information I want to give you all, that our next resource person, the resource person after Dr. Sourav Saha, she has her own YouTube channel, that is Exam Race, and due to some copyright policies, she will be hosting or live streaming her video session in her YouTube channel, which I am posting after every 10 to 15 minutes in the chat boxes. And also, I think many of you have got the email. So for the next session, from around 12 or 12:30 onwards, please, if you are not able to see her on the Zoom platform, please do visit her YouTube channel, which I am continuously posting on the chat boxes. Thank you. And Sourav, welcome you to this webinar. You are a younger brother to me and very dear. You are one of the very few geniuses. And I'm so happy you accepted my invitation at a very short notice. And I would just hand over to you the platform to the next session of lecture. Thank you. And you may start.
So I should start?
Yes, yes. I would request all other participants to please mute yourselves.
Okay. Can you see the screen?
Yes, Sourav, yes. Absolutely fine.
Okay.
You're audible as well.
Awesome, great. Thank you for the good lectures provided by the faculties. Hello, everyone. Good morning. Suprabhat. My name is Sourav Saha. I'm from Jalpaiguri, West Bengal, basically. Then moved to Delhi and now in the US doing my research. So today I'll be talking about glaciations in the Himalaya and Tibet in the last 15,000 years. So 1,000 years is generally noted by K. So K, whenever I will say Ka, so K is 1,000, A means annum, which is basically year. I'll be talking about some of the challenges and some of the promises of this project that I recently finished during my PhD. My entire lecture would be in English. However, if you have any questions, please ask. And maybe Abira De or Devabrata can stop me anytime. I'd be happy to answer those whichever language you want. I mean, I can speak 3, so I can be flexible in giving answers in 3 different languages. Anyways, with that, let's get started. So because many of the audience here are students who may or may not know much about glacial geology, I thought to start with some basic concepts so that it makes clear to you what I'm talking about and how we are going to address these issues. So this is the background picture is a picture of the Mount Everest, and this is the glaciers. One thing, can you guys see my cursor rotating on the screen? Maybe someone can just say.
Yes.
Okay, great. So this is a glacier, it's called Lhotse Nuuk Glacier. The glacier has a sort of like amphitheater shaped accumulation zone. It's called glacial cirque. Accumulation is zone, basically you have accumulation of snow, and yearly basis you have net accumulation. In other terms, the net accumulation means you have some accumulation and some melting. Accumulation you can think of during the winter, and melting you can think of during the summer, but overall you get net accumulation. That's what's happening over this upstream section of the glacier, or upglacial section of this glacier. Down the glacier you have this area where you have net ablation. In other words, you have more melting in a yearly basis than you have accumulation. So these two zones are distinct from each other in terms of how they operate. And they're also important in terms of maintaining the health of a glacier. So if you have more accumulation, you can think of that there's a net accumulation increasing in the ablation zone. So overall, the glacial would grow in time, which generally happens in the colder period of time. In layman words, think about ice ages. When you talk about ice ages, it's colder, more snow, net accumulation is happening. That's why the glacier is growing, similar to the ice sheets. Whereas if you have warmer time, for example, at present, you have warmer temperature causing melt in glaciers. So you have net ablation, and that causes the glacier to shrink or recede over time. Same thing with ice sheets as well. So these are the two important concepts, and where the accumulation zone and ablation zone basically meet or balance each other out, that zone is called the equilibrium line altitude. And I'll come back to this concept of equilibrium line altitude and several times during this talk. Some of the glacial landforms that I'll be talking a lot in this talk are moraines. So moraines are basically conical shaped hills. So you can see that this is the present altitude of the glacier, and high above there's this conical shaped landform. It's over here too. So because these kind of moraines are lateral to the glacier body, we call it as a lateral moraine, where the glacier basically stops or ends, and then they start accumulating all the sediments and boulders that they carry from upstream section or up glacial section. Then they deposit it over there at the end or the terminus, and we call those moraines as end moraines. So this is a zoomed in section of an end moraine, and you can see that here. Let me minimize it. Oops. So let's see. Yeah, there you go. You can see that they looks like this conical hill-shaped moraines, but they're mostly in the lobe shape. So these are the distinct from the lateral moraines, and depending upon the moraine types, they tell more about when the glacier was advanced, when the glacier was receded, or if the glacier was stable. So those are the important concepts. Need to get rid of these. I think they are blocking my screen. Anyways, I don't know how to do that right now.
What is the problem, Sourav?
Can you guys see the screen fully, or you can see like some, like I can see like some screen showing someone waiting to admit?
Oh no, yes, that's coming. We'll see if you can remove it.
Yeah, I don't know how to drag. Oh yeah, okay. Yeah, I think I can drag something. Okay, yeah. So you can see that. So there's two more concepts that I want to, or one more concept I want to say. Whenever we talk about glaciers, glaciers is a moving body of ice. So any moving body of ice that has multi-year net accumulation of snow is basically defined as glacier. So this one is a glacier, but a chunk of ice over here that is not moving is not a glacier. So always keep that in mind whenever we're talking about glaciers. This is a moving body of glaciers. I've already talked about moraines and its characteristics, and I'll be using that landform mostly throughout this talk. Okay. So basically, glacial landforms could be depositional or could be erosional landforms. These landforms can be dated using radiometric dating methods. Basically, that radiometric dating methods, if you don't know much about it, it helps us to determine the time of that landform. There are many different types of dating methods. I am mostly using radiometric dating methods. So for example, here, again, the Longitudinal Glacier, you have these moraines and you have this huge boulder sticking within the moraine. So basically, I or our team will go over these boulders, collect some samples. And I'll explain more how this dating method works in my subsequent slides. So that's what we'll be interested to do more of like a cosmogenic nuclei dating in those boulders. Sometimes you have moraines, and in between moraine deposit, you can see a relatively dark organic rich layer. You can see that I'm scrolling through my cursor here. This is basically a past soil, or we call it paleo soil. You can do like radiocarbon dating on them, and then you can determine when the soil was formed. So that gives a maximum time when the soil was formed. So I'll use generally those techniques to basically constrain when the moraine formed and how I can infer glacial information from that. So to summarize, what I basically covered so far is that glacial landforms record past glacial history. Landforms can be dated using any radiometric dating methods, for example, cosmogenic or radiocarbon, and there
Participants, kindly unmute yourself. Sorry, mute yourself.
Okay.
Kindly mute all the participants.
I'm now clear, ma'am. Please continue.
Someone raised a hand. Not sure if you're accepting any questions at the moment.
We are looking into the chat box, Sourav. I'll loan down the questions and I'll tell you later.
Okay, sounds good. So basically, to summarize again, so glacial landforms record the past glacial history. These landforms can be dated using cosmogenic or radiocarbon or other dating methods, and there are several different types of dating methods that you can apply. The timing or the dates of these landforms help us constrain the timing of past glaciation, meaning when glacial advance or remained stagnant for a while or retreated. Okay? So past glaciation may be linked to paleo-environmental changes, for example, changes in the climate. And we can use these past glacial information as an analog for future climate change. And that's this project is all about. Okay? The motivation for this project started due to a couple of misinformation and controversies that actually raised in the early years, starting from 2007. So IPCC, which is the Intergovernmental Panel on Climate Change, came out in 2007, and they infamously quoted that the Himalayan glaciers will be disappeared by 2035. Now they retracted that code just because it was based on faulty information. In response to that, Indian glaciologists came out and they proposed that many of the large Himalayan glaciers today are responding to climate shifts that has taken place 6,000 or 15,000 years ago. While both of the concepts both of the codes are wrong, and I can explain to you why. One is based on, the IPCC report was based on limited studies. The other report is based on only a few glaciers looking at a scale that's basically extend from 100,000 years or more. So they were talking about changes and glacial response at the time scale of 6,000 or 15,000 years. Usually glacial response times vary from several hundred years to 1,000 years or so. They are not distinct by, not differed by several thousands of years, which is kind of a wrong sort of understanding of these glaciers. Now, what the present study shows is that the Himalayan glaciers are not responding in a similar pattern to the uniform changes in the climate. For example, one of the famous types of glaciers are the Karakoram Glaciers, called Karakoram Anomaly. And if you can see over at the lower panel, there are two photographs. This is from Rika Samba Glacier from Nepal. See, from 1974, between 1974 and 2010, this glacier is almost gone. Okay. Now look into the right side panel. This is the Kichak Kumdan Glacier from Karakoram. See these two glaciers, the terminus of the snout of this glacier. So what is happening is that over a course of just a few years to decade, these glaciers actually advancing, whereas the other glaciers remain stagnant. This is called Karakoram Anomaly, that these glaciers are actually either stagnant or advancing. Now, these glaciers advance because of glacial surge, which is a different concept. But overall, what it shows is that not all glaciers in the Himalayas are responding in a similar fashion, even though there has been uniform increase in temperature. Now, a few studies that came out in 2015 and 16 concluded also that the Himalayan glaciers or Himalayan glacial advances are probably out of phase with the glacial advances experienced throughout the Northern Hemisphere. Now, this is a critical point they made, because if the Himalayan glaciers are not going to respond in a similar fashion, then we need to know what's going to happen in the next 100 years or so. Few other research gaps that I wanted to point it out are like limited. So basically, most of the studies either looked at the catchment scale glacial response. So you look into small glacial catchments and basically looked into the catchment scale glacial response. Other studies looked at the region-specific response, but those region-specific response are not robust, and especially for the Holocene timescale. So we don't know so Holocene, basically we're talking about last 11,000 years. I can see someone is drawing on my screen. I don't know, I don't have any, okay, that's gone, great. Let me recap again. So basically, we don't have Holocene history, good Holocene glacial history. Holocene is basically the last 11.7 thousand years. Since my talk is mostly about late Pleistocene and Holocene, so we're talking about mostly that period of time. There are other issues of that, and that's the issues with the dating. So basically, there's a problem with inheritance, and I'll explain more about what we mean by inheritance. There's also a major problem across all the different dating methods is that the large relative error. So many of you who knows about simple statistics, you have a mean and you have a standard deviation. So we generally, when we get an age of something, we get an age, which is basically the mean, and we get 1 sigma or 2 sigma, which is basically the standard deviation. So you can think of a normal distribution graph, you have mean in the middle, and you have sigma distribution on both the sides. So basically, if you have a boulder that has a mean age of 100,000 years with an uncertainty of 10,000 years, the only relative error is only 10%. But if you have a younger boulders that has a relative error that's like, so mean is 5,000 years and relative error or error is 1,000 years, you already got 20% error. And this generally increases a lot as you go towards more younger ages. We also do not know about the timing of Little Ice Age. So Little Ice Age is when we have the more extensive glacial activity throughout the world. And generally it's between 16th and 19th century. Because of these problems with the dating methods and our understanding, we basically still do not know the timing when the Little Ice Age happened in the Himalayas. However, the Himalayan glaciers has a lot of potentiality. They are widespread, they're well preserved. Specific questions at the shorter time scale about their dynamics can be addressed. So we are talking about 1,000 years or less. So just to give you a perspective, when we talk about glaciations, people think about several 100,000 years. So like, for example, the last glacial cycle was 100,000 years, okay? So when we talk about the shorter scale impact, we do not know much about it, but the Holocene glacial history or the glacial history for the last 15,000 years have the potentiality to inform us more about them. And they are basically much more helpful analog for future climate change, because we are more interested in what's going to happen in the next 100 years. A study that only addressed glaciation in 100,000 years time scale may not inform us much about what's going to happen in the next 100 years. So with that, I focused my studies in the Himalayas. These are, as you know, tropical high altitude mountains covered by glaciers, and these are called, this area is also called the third pole of our planet Earth. Just to give you a simple sort of description of the tectonics, so you see different mountain ranges. This is a cross section from south to north. You can see the Indo-Gangetic plain over here. As you crosses these different mountain ranges, you basically crosses the Indian portion of the continent. So basically you have the lower Shivalik or Shivalik over here. You have the main boundary thrust differentiating the lesser Himalaya from the lower Shivalik or the sub-Himalaya. And you have the main central thrust differentiating the higher Himalaya from the lower ones. And you can see that at the higher Himalaya, you have the highest altitude. Now, this is not to the scale, but you can see that in relative scale, it's still the highest elevation. This is part of the Indian continent, and you have then the Tibetan part of, or the Eurasian part of the continent, which is basically Tibetan plateau along the suture zone. Okay, so mostly the average elevation from higher Himalaya and the Tibet is 5,000 years or a little lower than 5,000 years along the Tibet. Now, this is important, and I wanted the reason I wanted to show you is that you have to remember this south to north gradient of altitude, because many of the things that I'll show you or I'll present in my next slides is related to this south to north gradient. The bigger questions that I'm interested in is that how glaciers respond to uniform climate forcing across these different different ranges in the Himalaya and Tibet. So let me first show you the prevailing climate system in this area. So this is a hillshed map, and superimposed on the hillshed map, you have these satellite-derived precipitation map. So anything that shows towards the red, you have much lower precipitation. Anything showing in the blue, you have much higher precipitation. So you can see that in animation, I'm showing that the cloud, or which is basically representing the main climate system, this is monsoon bringing moisture from the Arabian Sea and Bay of Bengal to the origin, the Himalaya and Tibet. You have some moisture coming from the eastern China Sea, and it's mostly influencing the eastern section of the Tibet and part of China. Excuse me. In the winter, you have most of the moisture coming from the Mediterranean Sea by the mid-latitude westerlies, and it's only happening during the winter months. And you have some dry and cold air coming from Siberian high from the north. Now you can see that most of the precipitation are concentrated over the Himalayan range. And if you just follow the altitude, again, you can see that south to north, most of them are basically sort of covered or blanketed by these high altitude mountains. They have more precipitation over there. When the air mass crosses that elevation and then goes to the other side, you basically create a rain shadow zone because they're depleted of moisture. So as we move further, or as these air masses move further towards the interior of the Tibet, you have less and less rainfall. Now, again, remember the transect that I'm drawing here, south to north, because I'll go back to it a little later. So there's a huge orographic gradient in terms of precipitation and temperature. In this figure, you have, and you have to just orient yourself into a different way. So you have south is showing this way. So south looking at Bay of Bengal, and you are located at the Tibet. So this is north and this is south. This side is Pakistan, and this side is your the China, the eastern China area. So if you orient yourself in that way, you can see that this is a temperature 3D construction, and this is a precipitation 3D construction. All the values are normalized by the maximum. Here again, you have lower latitudes over here, so that means that's close to the equator, so going south. You have there's a increase towards this way, the eastern longitudes. So you can see that there's a strong gradient both in terms of temperature and precipitation. The temperature is higher towards the south, okay, where you have much higher ranges. As you move further towards the north, the entire origin, mostly the Tibetan sections, become very, very cold. For precipitation, you have much higher precipitations again in the south. As you move further towards inland, the precipitation drops considerably. So you can see that there's a strong climatic gradient, mostly in terms of temperature and precipitation. And these are important because they basically define the characteristics of different glaciers. So what do I mean by that? Let's look into this photograph, the sketch here. So here you have again the different mountain ranges. So you have the Greater Himalaya here, Lesser Himalaya here. moving towards the Tibet. So again, south to north gradient that I draw in my previous slide. You can see that the glaciers over here are much bigger. And as you move towards further inland, the glaciers become smaller and smaller. The glaciers in this area looks more like this. They look a little dirty. They have a lot of boulders, a lot of sediments covering these glacial surfaces. As you move further towards the north, the glaciers becomes more cleaner, or you have more clean ice and less of this debris. These glaciers over south receive most of their precipitation from the monsoon and some from the westerlies. They are warm, they are moist, they are technically called temperate glaciers. They are highly susceptible to changes in the temperature. So they're temperature sensitive glaciers. As you move further towards the north, glaciers become cold based. They are cold and dry, and they are more sensitive to the changes in precipitation. The reason being, one receives more precipitation, so they are more sensitive to the temperature. Another receives less precipitation, so they are more sensitive to the precipitation. So with that, my strategy was to look into different glaciers located at different settings that receive different temperature and precipitation. So these red boxes are the new study areas that I did for this project. And all the yellow ones are the studies that already been published by other people. I generally compile the studies that only used cosmogenic dates in their analysis, largely because the radiocarbon materials or the organic materials are not common in the high altitude glaciated environments. Since the soil formation takes a longer time, they don't have vegetation over there, so you don't have a lot of organic materials. So mostly I focused on the cosmogenic dating for my project, and I'll explain to you how the cosmogenic dating works. All these circles with white and black are the new study areas. I numbered them from 1 to, I think it's 36, 37 valleys. So there are total 73 valleys, glaciated published valleys, and 7 new ones. Again, the background map is all the precipitation gradient showing in the higher resolution. And all the air mass is showing by different arrows. So my study areas, if you look at it, it located one, which is located further south. This is more temperate, warm, moist glaciers. And then gradually I'm moving further towards the inland or north, where the glaciers are more cold based and more sensitive to precipitation. So I'm covering this entire different gradient in my research. Again, for this talk, our focus is to only discuss about last 15,000 years. And there are a couple of geologic time scale that I think would be helpful for students to know. So basically, when we talk about late glacial, anything that's above 11.7 thousand years until 16,000 years, this period is known as the late glacial time. Then you have the early Holocene. So instead of the Holocene, you have, that's basically your 7.3 to 8.2. Sorry, 11.7, 8.3 to 11.7. That's your early Holocene. When I talk about mid-Holocene, that's basically between 8.3 to 4.2 thousand years. And the late Holocene is basically 4.2 to present. Now there's one more concept that's still debating is Anthropocene, and I can talk to you more about that if you needed to. But basically, these are formal technical terms, and we'll be using that throughout the presentation. So the hypothesis that I am testing in this project is that the glacial activities in the Himalaya and Tibet are largely dominated by climate change, specifically by the summer monsoon. And what do I mean by that? So if you focus on this graph here, so you have time from 0 means present and 16 means the 16,000 years. So time is increasing this way. These are different climate proxy data. Some of them are, so this one is showing the ambient temperature. This is from the Gulia ice core, delta 18 isotopic data. What it means is that you have lower temperature as it's moving towards this way, higher temperature towards this way. Now this graph over here, the black and red is are actually proxies for the monsoon precipitation. This is delta 18 from stalactites and stalagmites. This is from Sanbao Cave, China. So what you can see that with the values, so if you are going towards higher or the heavier isotopes, then you have much more stronger, much more heavier, then you have much weaker precipitation. And if you're going towards the lower values, you have much higher precipitation. So you can see that along this transition of the Holocene, you have a jump in precipitation, and then precipitation is gradually declining. This dotted curve is the insolation for the northern hemisphere. So the orbital forcing curve is showing the solar activity. So you can see that along this Holocene transition, you have increase in the insolation curve and then decrease. So the monsoon is basically mimicking what is going on in terms of insolation curve. I'll get back to you later in the talk why these are all important. So basically, what we should expect if our hypothesis is true, that during enhanced monsoon, we should expect to see more extensive glacial advances if our hypothesis is true. Again, now precipitation sensitive glaciers should show relatively stronger response than the glaciers that are less sensitive to precipitation. Okay, so let's see if we can actually test the hypothesis. A couple of assumptions before we go ahead. So in an idealistic scenario, you have a glacier, showing it here in lighter color, and you have these black lines basically showing the moraines, the lateral and terminal moraines. So in idealistic scenario, you should preserve all the moraines. But in nature, it doesn't happen because the glacier basically advanced and retreated. So when it advances, it basically gets rid of any older deposit, so on and so forth. And also the moraines degrade by itself, sometimes covered by these talus deposits or debris flow deposit. So in nature, what we get is basically a messy picture. We get some of these moraines, that are preserved, but not all of them are preserved. So one of the things that I basically did in this study is that instead of just focusing on one catchment and saying that this glacier advanced only 2,000 years and 1,500 years ago, I am actually looking at the overall picture of all the adjacent glaciers. And what I could find is that different valleys with different glacial activities preserve different periods of glacial landforms. So I can combine them and then I can get more of a regional picture. So this is what I'm doing most of my studies, that I'm focusing on several adjacent catchments and then I'm combining them to get a more robust information of glacial activity. So whenever I talk about local glacial stages, I will be talking about these adjacent valleys that I'm combining. When I'll be talking about regional glacial stages, then I'll be talking about not only just 2 or 3 adjacent glaciated valleys, but several glaciers in a regional scale. So one of the best part of doing this project was to do the field work. And I was thinking to show you some of the cool photographs and some of the cool activities that we did during this project. So logistic is a big, arranging a logistics for extended fieldwork in the Himalayas is always challenging. So you have to rely on ponies. Sometimes you have to carry all of your gear by yourself. And it takes a lot of physical endurance to finish all this work. But you go in these very high altitude areas, you enjoy the nature, the snow. Even in the short distances, the climate changes dramatically. So this is a picture of Solang Valley near Manali in Himachal Pradesh. So this is over 4,000 meter altitude. We're collecting samples. There was wet snow, windy situation, not good for any activity. When we came down later in the day, just only 5,000 meters down the valley, and it just turned into just like pure downpouring, just water, rain. So as I can show you here, that this dramatic change in how the mountain climate works. But that's also fun because at the end of the day, when we come back, we have like the best food ever. Sometimes we don't have much funding. So like this trip we did in Hamta Glacier in Lahore, me and my friend basically find these 2 guys. They were coming in the same area. We just jumped into the back of the pickup truck. And it was not fun, but that's how we roll. Then we cross cold streams. Sometimes you have to cross these sharp glacial faces. So this is actually a snout of the Barasinghi Glacier. They might sometimes give you the impression that it's very challenging. And yes, indeed, it is challenging. But at the same time, it's also very satisfying as a geomorphologist working in this area. So the whole point of us going in these high altitude areas and doing all this stuff is to start with the mapping of that area. So first thing we do is to develop a robust geomorphic mapping of each individual catchments. So the approach I apply is that I make reconnaissance geomorphic map using satellite images, Google Earth, and then I go to the field and then I verify all the landforms that I actually found. So we map the glacier, glacial snout, we map all different types of moraines. So these are all the lateral moraines, all the eroded surface, which moraines cutting which other moraines, because all these concepts are important, because at the end of the day, when I see that, I see this moraine is inset within this moraine. So this would be an older age moraine compared to this one. This moraine is cutting across this moraine. So that means this moraine is younger than this one. So these information are first order information that I'm mostly interested. Once I have a framework of relative dating, then I go and basically collect samples from these boulders, or from these moraines. Multiple samples from each individual moraine, depending upon how they are available. And also needed to do one thing, it's called sedimentary analysis. Sometimes we can be misguided, or we can just think that this is a moraine, but in reality, that might be just a slope deposit, which were later eroded by the glacier. So you need to do some sedimentological analysis in the field in order to confirm that, yes, this is a moraine, this is formed by glaciers, and these boulders are indeed deposited by different glacial activities. So the dating method that I use, and I mostly use in this talk, is called cosmogenic dating, or in other words, the terrestrial cosmogenic nuclide dating. The way it works is that you have the primary cosmic rays coming from the space. Basically, anytime stars are dying, nebula activity is going, they're releasing high energy cosmic rays. These cosmic rays then bombard the atmosphere, and these primary cosmic rays are so high energy that they basically, it's like a bullet that goes through the magnetic field, and then basically have a second shower of cosmic rays. They basically bombard with the atmosphere or the molecules that basically create a nuclear reaction, and that creates a secondary cosmic rays. So if you are at the surface, whether you are a human or a rock or a boulder, you are receiving these cosmic rays consistently. Okay, so we can measure the concentration of these cosmic rays, and basically these cosmic rays are concentrating in a exposed surface or exposed boulder. In our case,
B5.
So these cosmic rays are concentrated at a rate. So we know the rate. So if you know the concentration, then we can actually figure out how long that surface is exposed to cosmic rays. One of the main method of nuclear reaction is spallation. So spallation is basically a breakup of bombarded neutrons and protons. So these cosmic rays, when they're bombarding these molecules here at the surface, they're concentrating they're transforming into different neutrons and protons and creating different isotopes. For example, beryllium-10 is one of the isotopes that often form in many minerals. And the minerals that we are mostly interested in is called quartz, SiO2. Quartz is everywhere. It's more stable, and they're accumulating this beryllium-10 as long as they're exposed to the cosmic rays. And you can see that it's a depth-dependent factor. So as you can see at the surface, you have very high spallation going on. Whereas as you go down, the spallation basically decreases, or we call attenuated. So we basically collect samples from the surface because that's the most representative of how long the sample has exposed to the cosmic rays. And we plug it into this simple equation. It's basically N10 is nuclide concentration. So we measure how much nuclide concentration is there. we know the production rate. We measure it in a different ways that I would be interested to talk more about it if you're interested. And we also know the decay constant. So these cosmic rays are also decay over a period of time. So once we plug in all these things, we can basically get what we call the time component, which is shown here by T. So you can just rearrange the equation to get the T, or the time. In a glacial settings, how it works is that, so you have a upper bedrock wall, right? So you have the glacier, this is the cirque, and the glaciers coming. This is showing in gray, the entire glacier. So all the boulders here are basically dislodged from the bedrock by frost cracking, all the periglacial processes. They are then entrained within these glaciers. Some of these boulders are coming from the bottom or the bedrock or the depth. These boulders are then eventually in the accumulation zone, they're eventually transported to the ablation zone. And in terms of, these are called supraglacial transportation because these are on top of the glaciers. These boulders transported eventually. While they transport, they basically rotate, get eroded, broken down. And what we basically assume is that during this process of transportation, either through supraglacial processes or subglacial processes, which is through the bed and glacial interface, these boulders actually either completely eroded or have not seen the cosmic rays before. So what does it mean that when these boulders get deposited in moraine, so this is showing a moraine here, these are then basically freshly accumulating the cosmic rays. So then I can just come here, collect the samples from the surface, and this exposure date of these boulders or several boulders from this moraine would gives us a minimum age when the glacier was there. So see how it works. So more time the boulders have spent, the more the beryllium concentration and more the older the age. So for younger ones, I should expect much lower concentration of beryllium-10. And a couple more technical concepts. So again, I mentioned equilibrium line altitude. So you have accumulation zone and you have start of the ablation zone. While you have balance, you have equilibrium line altitudes or ELA. Now think of these glaciers currently over here, but in the past, the glacier was over here, right? So that means the ELA was also down than what it is present. So we can actually then map out the older glacial extent, and using different methods of ELA, we can basically then estimate the past ELA. So the change from present to the past ELAs basically gives us an idea of glacial extent, or what we call amplitude of glaciation, meaning how far glaciers have traveled. Now, we can also do a length measurement, but I'll explain to you why length measurements are often misleading, whereas ELA or delta ELA, which is again present minus the past, is more useful to understand the extent of glaciation. So now I'm introducing you two parameters. One is the timing of these landforms, and second one is the extent of this glacial advance. Okay. Now, the problems with the cosmogenic dating specifically is several. So you have these boulders of bedrock already exposed to the cosmic rays, right? So they're accumulating cosmic nuclides over a period of time before entrained in the glacial system. So longer the stay, the longer the concentration, which we call inherited concentration or inheritance. Now, this is not a problem for boulders that's coming from the bed glacial interface or subglacial zone. But for other glaciers where we have, or for upper glaciers, the supraglacial surface processes, you should expect to have some of the concentration already inbuilt within these boulders. Now, I told you that our assumption is that these boulders, when they are rotated and transported in the glacial system, get eroded enough that anything that accumulated at the surface is almost gone. So they are almost freshly getting the cosmic rays. But if that doesn't happen, if the boulders are transported without getting eroded, then ultimately they have an older concentration from the bedrock and newer concentration from the time they were exposed. So in that case, the inheritance would give us a overestimate of the age. Now, there are different ways we can also get underestimate of the age. For example, if you have a weathering or erosion, you can see that the rocks here is broken down. So if you're broken down, then surface concentration is gone. So ultimately, you're losing the concentration. So it will give you a younger age. Similarly, if you have a moraine that looks like a conical shaped hill, and it has some boulders. So when these boulders are in between the moraine, it's shielded from the cosmic rays. So it's not receiving any cosmic rays at this depth, right? But over time, what happens is the moraine degraded, it becomes conical to rounded hill. So these boulders then actually exhumed to the surface, and then they start receiving cosmic rays. So if someone is not much careful about it, they will get an age which should be much younger. So these are the two ways you can even get younger ages, exhumation and erosion. Now, for 15,000 years moraines, these two problems are really, really negligible. So we can basically deny or completely disregard these two ways of getting younger ages. But inheritance is a huge problem. Think about, again, if you have 100,000 boulders and it has, say, 1,000 or 2,000 years of inheritance, you basically don't see it when you basically get the entire uncertainty. But if you have 1,000 boulders, 1,000 years boulders, and if the boulder has an inheritance of 300 to 500 years already, you are estimating an age of 1.5 thousand years. So it's already offset a lot. So that is a big problem with the current dating methods. So that was one of the things that I tried to address in this project. So we basically go in the field, we find the best possible tabular shaped boulders that has not been fractured, eroded, or any way, shape, and form weathered. They are more stable. We collect a bunch of samples from a bunch of these moraines, and we basically get the ages for that landform. In terms of amplitude, I already explained that we use those landforms to get the map of the glacier. So for example, here the lighter color is the present glacier of the Gangotri, present glacial map of the Gangotri glacier. This is the current ELA. And in the past, based on the moraine stratigraphy, the glacier was over here, then over here, then over here, and over here, and so on. So we can then use these maps and estimate the ELA change. So we can not only get the timing, but also the extent of these glaciers at different point of time. We can also use the medial flow length of the glacier. And I'm cautioning again that using the length in its rudimentary form could be misleading, and I'll explain to you in the next slide why. Whereas ELA doesn't have all those problems. Another thing you should also take into note are the hypsometry of the glacier. So hypsometry is basically your altitude versus area. So here the area is normalized. So what it means is that it basically shows that if you have a larger area concentration at different altitudes, so with different ELAs, the glacial behavior would be very distinct. So for example, this glacier over here has a very different ELA compared to this tributary glaciers. So their response is likely to be different. So we also take into account the changes in the hypsometry. For all these glaciated valleys, including the new ones, I also estimated the change of the length. And so here you have the length change showing in the y-axis, in the x-axis, different numbers. So these numbers are different glaciated valleys. And what you can see here is that the blue one is the present length, and the diamond here is showing the past length of the glacier. Now, if you're simply using the length, it is misleading because it depends on the size of the glacier, types of the glaciers, or thermal properties, or either it's a cold-based glaciers or temperate glaciers. It also depends on the glacial hypsometry, slope, like how steep is the slope of where the glacier is flowing. Also subglacial processes, because some glaciers has more of like a subglacial streams. They allow the glaciers to move faster than the other glaciers. So all these factors, and also the microclimate, they impact the length. So length by itself is not a good proxy for estimating the extent of glaciation. So we are focusing mostly on the equilibrium line altitude, or ELA, for the entire project. So this is the Gangotri glaciated valley. So I have, let me go back again. So I showed you that there are several glaciated valleys that I studied, but I'm mostly focusing on Gangotri over here, just because we don't have much time to go over all the details. So this is one of the largest glaciers in the Himalayas, 32 kilometers long, and most of you know that this is the source of the Ganges. For these glaciated valleys, we already have very good data set for the older glaciations, but we do not know much about the younger glaciation or younger glacial history, younger than 5,000 years. So I was interested to look into more about what is going on in the younger times, because that is more important for the health of this glacier and for the overall project. So first thing, again, we identified different moraines. We mapped them out. We know the relative ages. So this one is younger than this one. We collected samples and then we processed the samples. We also know that some of these moraines are actually historical moraines. What historical means is basically that older explorer, the Geological Society of India explorer, they went in this Gangotri glacier in the past. They demarcated them in their notebooks. So we know that the age of some of these landforms. So that is important because I talked about inheritance, right? So since we already know the exact age or roughly the exact age of these moraines, we can collect boulders from these moraines and basically see that compared to this age, what's the age difference we get in our by our cosmogenic nuclide dating. And that difference would tell us how much inheritance each individual moraines could have. And that could tell us more about whether we are actually getting the good signal or we're getting some wrong signal. Okay, so with that, so now again, I'm plotting here all the ages. The ages are in 1,000 years. As you can see that this younger moraine, 1935, I got ages of 200 years almost consistently. So this means that this has a little bit of inheritance, but considering the uncertainty, this inheritance is negligible in geologically speaking. We got other moraines similar. So 1780, we got a moraine boulders 200 to 300 years, except one outlier. All the ages are pretty consistent in most of the other studies, as other areas as well. So what this tells us that this technique does work. It gives us consistent ages that has an inheritance of only 50 to 100 years in the maximum case scenario. So that is not bad because sometimes we can get an inheritance of several hundreds of thousands of years, which is not the case for these kind of glaciers. That was interesting to at the start of the project because we had a much robust glacial retreat or advanced history. So basically what it shows is that you have a glacier that advanced over this period of time in 500 years ago, so remained stagnant. Then basically after that, the glacial retreated, remained stagnant from these moraines, retreated, remained stagnant from these moraines. And ever since, it's just continuously retreating in the last 100 years or so. If I plot this in a cross-sectional way, so this is the cirque at the top, and this is the down valley section. All these are location of different moraines. And as you can see that, and these are ages. So this is older age, 6,000 years, and you're going more towards the present. So you can see that consistently the ages are getting younger, which is what we expect. All these lines are equilibrium lines. So this is the mean with the uncertainty of 1 sigma. So this is the present equilibrium line. This was in the past. So it's going like this way. So what is interesting here that I would like to focus you is that the ages are almost consistent. They're consistently going younger. They matches really well with the historical dates, but they also show that in the last 2,000 years or so, the equilibrium line altitude did not change much, meaning these glaciers actually did not respond at a rate that is alarming to us. It is receding, but it's not responding in a huge manner. Even in like 5,000 years time scale, these glaciers have retreated, but there's barely some changes in the equilibrium line altitude. So I would not be surprised for these glaciers to retreat a little bit more and then basically stabilize at some point. But that's a matter of how you perceive the data and interpret the data. So now I did that analysis in all other 6 glaciated valleys. So here I'm showing ages in the x-axis. This area is the Gangotri glaciated area, located further south, right? Gangotri and Meru, these are temperate glaciers, more sensitive to temperature change, okay? Now, glaciers over here is located further north. They are semi-arid glaciers. Cold-based glaciers does not do much of erosion at all. And you can see that when you see the younger ages over here, they're pretty well clustered. Whereas in these areas, the spread in the data is huge. We're talking about several thousands of years of spread. And this is what we call inheritance causing a lot more spread in the data. and this doesn't allow us to actually constrain the edges better. Now, this region is the in-between region, so they have the characteristics, some of the characteristics of this kind of glaciers and also this kind of glaciers. They shows that overall, if you look at it, there's improvement in edge constraint as we move further towards the south, where the glaciers are much more erosive, they're temperate, and they're more sensitive to temperature. Overall, what we see that there's one late glacial advance, 2 early Holocene advance. These are, I'm talking about all the local glacial advances, 1 mid-Holocene and several late Holocene advances, 14 of them. So overall, the large polythermal to temperate glaciers, which is the glaciers over here and some over here, they are very good to constrain younger ages compared to the glaciers that located further north because they have much more scatter. Now, this is a cumulative density plot. Here in the x-axis, you have the ages. In the y-axis, you have the cumulative distribution from between 0 to 1. So basically, I'm showing the same thing which I showed in the last graph, but in a different way. So for example, if all my ages are well clustered, they would have almost a vertical distribution and less of a lower, older tail distribution. So except few of them, most of the glaciers that are from Gangotri area that are wet, warm, temperate, sensitive, they show very well clusters. It's compared to the glaciers that are located further in the north. So all these dry cold glaciers have much higher lower tail distribution, indicating again that the method that we're using for these glaciers may not be picking up the correct signal, okay? And that's why these glaciers can help us actually constrain the little ice age or last ice age than the glaciers over here. Again, thinking about the geologic processes, again, these glaciers, these boulders are continuously eroding, broken down. They are great, whereas glaciers over here, you can see that the boulders, they are barely get eroded. All these glaciers are almost clean. So again, it's pointing out the simple geomorphic processes that's going on in this kind of setting. So now I constructed the local glacial stages in my new studies. The next step was to basically compare all the study areas and see what is going on throughout the origin. Now, the first problem with comparison like this is that there are different types of glaciers. Again, referring back to the previous slides, you have glaciers that are much more wet, warm versus the glaciers much more cold. So how do we basically differentiate them based on climatic region? So, this map, again, this photographs again reiterating the same point. So you have a complex climatic system across the Himalaya and Tibet, and you have different complex glaciers across the Himalaya and Tibet. So we need to figure out a way to basically combine them. For that, we basically tried to do a cluster analysis and principal analysis based on glaciers and climate parameters. So what we did basically, we collect, so there's a bunch of glaciers already mapped by the glacial inventory. So these white polygons are basically each glaciers. There are over 42,000 glaciers that's there. So we basically what we did is that we use this glacier and use the GIS method to identify the midpoint of each polygons. Midpoint, we basically use that as like a dots, and each dots then we superimpose with the climate data, which is transferred into a gridded data. So then each point, by using this each point, we extracted the climate from each grid. And we did that for both temperature and precipitation. And we use all these different 9 parameters, climate parameters, to get an idea of how, for example, this glacier has different temperature and precipitation characteristics. And then we applied what we call the cluster analysis and principal component analysis. The way cluster analysis works is that it basically uses Euclidean distance between 2 data points. So for example, if a glacier has -10° annual temperature compared to a glacier that has -15° annual temperature, the Euclidean distance between them is higher compared to the glaciers that has, like, say, -11. So we can then basically cluster the glaciers that are close together and then differentiate the glaciers that's not close. So using the cluster analysis, I identified 5 different glaciated climatic regions. So this means that the glaciers over here is a distinct climate, then the glaciers over here compared to the glaciers over here and here. So this is a map, simplified map of all these glacial points. Excuse me. So you can see that this area, which is located much more interior of the Tibet, much drier climate, is distinct from the glaciers that are in blue, because this area still receives more precipitation than these ones. So there's a climatic gradient that we already explained or already showed that based on the different ranges of the Himalaya. So we then run the principal component analysis. So principal component analysis is basically a multivariable correlation. So when we apply a bunch of these different variables and then we ask the computer to basically estimate the principal component, the first PCI and second PCI basically should explain the majority of the components if they are indeed are correlated. So what we found is that when you compare all the PCIs, you can see that PCI also found that these individual groups that we identify by cluster analysis are indeed distinct. Now, there are a couple of outlier sections, outlier groups. So we basically get rid of these sectional outliers and these sectional outliers in green. So we have 3 different groups of glaciers, main types of glaciers. We call them different climatic regions, okay? Now, there's one problem, and that was that our method helps us to identify different climatic zones based on the latitudes. But there's also a longitudinal climatic zone. If you remember the climate system that I talked about, so you have more westerly influence over this side and much more East China Sea influence on this side. So we also needed to differentiate these 2 areas. So what we did, we then applied other previous studies that talked about distinct climate in these 2 different regions. So we then divided each region using this longitude into a more eastern section and more western section. And we've given them a number from A to 3. A1 and AB is the same climate based on this method, but then differentiated based on their longitude. And if you can see here, it's all the different climatic regions. So again, this one is arid and semi-arid climate. It's mostly northwestern Tibet, Pamir, Trans-Himalayan, and Tian Shan. Whereas this one, B, is again arid and semi-arid, but more of a southern and northeastern Tibet. Similarly, blue is the transitional climatic zone. Transitional central is the cyan, and in the red is we have wet temperate glaciers. Now, once we have this regional framework ready, then it's become much more simpler, because then we can basically combine all the glaciers that are located in each regions and compare them. The principal component analysis that I don't know whether we have much time, but I can get back to it again. Basically, what it shows also is that it also calculated eigenvectors. So basically, eigenvectors helps whether your variables has a positive relationship or a negative relationship. What we found overall is that the precipitation has a strong positive relationship in terms of differentiating different types of glaciers. Or in other words, determining different climate zones. So that is a good first order indication that our hypothesis is working. That means that precipitation indeed is a major influencing factor determining different types of glaciers. And if that's true, then we should expect to see different response of these glaciers based on their sensitivity. So now this graph is basically a compilation of all the data from all the glaciated valleys. Now I would like to simplify the figure again. So this is again, if you remember those proxy data that I introduced to you before, you have timing, present to 16,000 years edges. So you have proxy data showing over here. You have the ambient temperature in this light blue. You have precipitation proxy for the monsoon in black and red, and you have orbital forcing in dotted line. Here you have all the compilation of semi-arid climate. Now this is the Trans-Himalaya and the Northwestern Himalaya and Pamir section. So this one is different. 1A is again different from say 1B, which was more towards the southern and northeastern Tibet section. So, and in the x-axis here, you have what you call delta ELA change. So what is showing here that the glaciers that has higher delta ELA is over here compared to the glaciers that have lower delta ELA. Now, if you just focus on this figure overall, what do you see is that the glaciers have much higher delta ELA change during the late glacial. And gradually, there's a gradient that's showing limited glacial advances or limited delta ELA change over time. Now, follow this graph, this monsoon graph. It's almost mimicking the same pattern over time. This pattern is less distinct in other glaciated regions, and largely because we have limited data points to basically convincingly say something. We do see a rough sort of pattern, but to be cautious, we propose that more data is required to basically identify this general pattern in most of the regions. Now, each gray line over here is basically each timing of glacial advances. Now, these timings are basically, we group them together based on different methods like finite mixture model, this is statistical test, student t-test, and kernel density model. So these are based on these different statistical methods, these groups are differentiated from each other. And they, again, mention when the glacier was advancing and what period of time. So you can see that over different regions, there is some synchronicity in glacial advances, but it's more common, more towards like some areas in certain times than in other areas. This dotted line is tentative because we don't have more than 3 data points. So we generally assume that if you have more than 3 data points, that's more robust signal than if you have only 2 data points. So there's a lot of work to be done, but it does show that you have a huge glacial advance during the late Holocene, probably the highest ELA change. Then in the early Holocene, you still have highest ELA change, but that early Holocene advance is common in some areas, but in other areas, they are not so distinct. And that also talks about how these different glaciers are behaving at this different point of time. Now, there are a few more intricate details that would be difficult for me to present at this point. But if you're interested, I can give you my recent papers, and you can get it from Dr. Abira and maybe read more about it and get a better idea of how these different glaciers at different times are behaving a little bit differently. So to generalize, we do see that there are one late glacial synchronous advances, more extensive, and there are at least 5 Holocene, common Holocene advances at different points of time, mostly showing a very close correspondence with the proxy data. How much time do you have? Do you have until 12 or less? I don't know.
Yes, you can continue, Sourav. We'll let you know. There are many
Okay.
questions as well. Okay.
Okay, great. So now look into the delta ELA change across all these glaciated valleys. So delta ELA, if you remember again, we are getting the ELA from the present to the past. What you can see that at this late glacial time, you have much higher changes in delta ELA towards these areas, these cold-based, semi-arid, arid areas. Whereas in the more temperature sensitive or more precipitation prone areas, which is located further south, you have very limited change in delta ELA, right? Now you see the similar pattern during the early Holocene time frame. During the sort of like late early Holocene, there's still the same pattern, but we have very few data points to conclude anything. In the mid Holocene, you see that there's a little bit of change in the pattern, that the southern glaciers, again, these are more temperature sensitive glaciers, having much higher delta ELA change compared to the glaciers located further in the north. Again, following in the same, in the late glacial time, late Holocene time, you still see that higher changes in the more warm glaciers than the colder glaciers. For the last 1,000 years, which is basically the Little Ice Age, the response is a little vague. But overall, again, most of the data points are coming from the south, and they're showing the changes are still a little higher. Now, what I have not shown yet today here in this talk is that the monsoon is very high in the early Holocene. It's gradually weakening in the mid-Holocene and then gradually start weakening over the time. The temperature sensitive, the precipitation sensitive northern glaciers are responding very extensively, or they are responding very highly during this early Holocene time frame. In the mid-Holocene, when the monsoon is weaker, we have some of the colder climate, mostly induced by the Westerlies. Remember, the Westerlies bringing moisture from the Mediterranean Sea. So the Westerlies is actually much more stronger during the mid-Holocene. And what we can see is that during that point of time, the Westerly doesn't bring a lot of moisture. It brings a lot of snow. So the temperature sensitive glaciers are responding much higher, sorry about that, than the glaciers that are not so sensitive to temperature because they already live in colder temperature. So we do see a strong indication of not only delta ELA change with overall time frame, which is regulated by monsoon, but also a different response to different climatic systems based on which climatic zone this glacier reside. Okay, so these two are very important findings that we can get. Now, I told you that we cannot use the length directly to infer anything about glaciers because they could be misleading. But there are ways you can actually use the length data. You can model the data to infer other things. So what I did here, I estimated the medial length of the glacier. So L over here is showing the medial length of a imaginary glacier. And the blue one is the first moraine. So that would be L1 moraine. So it's at some point of time, glacier was over here. This Ln is basically the second or n number of moraines that's formed after or before this glacial advance. So I know for now that this is a present length, which is L. Sorry, L prime 1 is the length between the current, the most recent glacial advance, and then so on and so forth. So I can get different length information, and I can basically then use a simple model. It's called a linear flow model. That was developed depending upon the temperature, precipitation, and change in glacial length. So in a simpler form, you see DL, which means delta change or delta length change, T here for time. So DT means time change. So you are basically estimating DL DT. So change in length over change in time. And you use this equation is 1 over tau. So tau is basically your tau and C. C is basically, I forgot the, it's a long day. Yeah, climate sensitivity, sorry. Climate sensitivity and response time. So tau is the response time. So the response time is basically how fast a glacier will respond. It depends on the slope. It depends on the glacial characteristics and the precipitation of the glacier. So for example, a temperate glacier with higher slope would have a much lower response time than a cold-based glaciers with lower slope, okay? And C is the climate sensitivity. It works the same way. So meaning that if you have a colder glaciers with limited precipitation, that glacier would take much longer time to have a change in their mass balance than a glacier that receives lots of snow. So we can then incorporate all this into the model and basically get an idea that if I change that temperature, which is here is a capital T, what would be the change in length? And we can use that information in an invert formula. So where we basically interested in the change in the time, in the temperature using the change in the length. Remember, we only have length information. We don't have time information. So we are just inverting the same formula in a different way. Originally, this model was developed for other glaciers throughout the world. So this is a change of length over time, and then they basically plug in that previous formula and then inverted that and get a temperature. And what they found is that in the last few decades, the change in global temperature is same as or within the uncertainty range of the change in the length of glaciers in different areas. So we use the same information and now plugging in our length data and the time information and basically constructing a past temperature change in some of our glaciated valleys. And this is a graph over here is showing the temperature. So in the x-axis, you have again time. It shouldn't be years, it's thousands of years. And in the y-axis, you have change in temperature from present. So this is a relative temperature change in Kelvin. Now, we do not know the exact temperature change in the past. So the exact information that you will get from here is not at all informative. But what is informative is the change in temperature over time, so which is delta T, meaning that delta T, if you look into group A with glaciers that are more arid and semi-arid versus glaciers which is wet warm is here in group 3, you can see the change in temperature is much lower for this glacier than this glacier over here. And we're talking about, again, the early Holocene. If you look into the early Holocene at different climate, you see that the glaciers located in group 1A, again, arid and semi-arid cold-based glaciers, sensitive to precipitation change, showing much higher changes in their length amplitude compared to the glaciers located further south. So even the precipitation has increased, their length did not increase in that sense. However, in the lower part, we were expected to see much more change in this data, but unfortunately, with a large uncertainty, we couldn't resolve it. Only thing we could resolve it is this period of time between this distinct character of these glaciers versus these glaciers over here. And again, group 3 is again the middle lower portion, and group 1A is over here. So what we can infer is that Model T may not accurately capture the exact perturbation in temperature, but the sense of change by delta T is significant. The mid-Holocene changes over here may not be all derived by changes in temperature. Although our model simplifies the temperature because it uses a constant precipitation value to estimate the parameters like climate sensitivity and response time, that uses a p-value, which is precipitation value. If we change the precipitation value, then you don't have to increase the temperature, or in other words, decrease the temperature. You just increase the precipitation value and you will still would be able to see the similar change. So what we basically propose is that this past temperature reconstruction based on glacial length is not true, but the change in delta T basically signifies more of a change in the precipitation, which is one of the big parameters in our model, than the temperature itself. So lastly, to conclude, that I previously mentioned that one of the studies concluded by Solovina et al. In 2015 and 16 that the Himalayan glaciers are not behaving in a similar way, or maybe out of phase with the glacial advances in elsewhere in Northern Hemisphere. So this is a compilation of all the glacial activity in North and South throughout the globe. And this diagram, I call it clock diagram. So basically starting 0 means present and your ages are increasing over 1,000 years time scale. So you can see that here blue basically represent extensive glacial advances, whereas this sort of brown, light brown is representing less extensive glacial advances. And these are relative forms. So what you can see that across most of the glaciers in North America and in Europe, you have much higher extensive glacial advance during the late Holocene time, which is 1,000 years or less. You can see that happening over most of the areas. The question was, is the same in the Himalayas? What we found is that the timing of these glacial advances, which is shown here by this pie sort of diagram, is almost comparable to all these glacial advances. So that means that in terms of timing, the Himalayan glaciers are not out of phase. But in terms of extent of glacial advances, they show a reverse pattern than many of the Northern Hemisphere glaciers. And that largely because of the prevailing climate system in this area. So basically, in a broader scale, you have orbital forcing, which is basically modulated by solar activities. Whenever you have higher temperature, your intertropical convergence zone basically move further north because the landmass get heated up. So ITCZ move further north. As the ITCZ move further north, that basically creates a lot more difference between the landmass and the ocean, so stronger monsoon. More stronger monsoon, you get much higher precipitation, you get more glacial advance. On the other hand, when you have the the change in the ITCC or the weakening of the ITCC when ITCC moving south, monsoon weakens, you have some glacial advance largely because of the changes in the North Atlantic and the Mediterranean region. So that area changes, which bringing much more glaciation in Europe, is also bringing some glaciation in the Himalayas, but they are not as extensive as the ones in the early phase that are modulated by monsoon. So overall, what we could conclude is that there's a strong influence of monsoon in terms of not only the timing, but extents of these glaciers. However, they are also influenced by westerlies in the later part, but westerly seems to have more of a subdued, limited response than the monsoon. In terms of, let me go back to it later. So in terms of summary, so we see that at least one synchronous late glacial advances and at least 5 Himalayan Holocene advances throughout the Himalaya and Tibet. Glaciers in general shows that they are more extensive during the 15,000 years of late glacial and during the early Holocene, and then progressively they become more restricted over time following the orbital forcing and the monsoonal curve. Summer monsoon regulate the larger extent of glaciation, which in turn are influenced by the orbital forcing, as I explained to you before. The cold and dry glaciers located further north that are more sensitive to precipitation are also more susceptible to any changes in the climate, especially changes in the precipitation. Whereas wet, warm glaciers located further south are best candidate to resolve for high resolution dating of these landforms. So there's a couple of things that we covered. Ultimately, what we actually can see is that there's a huge potentiality of Holocene glaciation. So this graph is basically a bar graph showing time axis over here, and these color codes are different periods of glacial advances for the last 10,000 years. This is from Owen and Dortch, and as you can see that although there are some similarity in some sort of glacial advances, but regionally there is no consistent pattern for the older Holocene, older than Holocene glacial advances. What I showed you in my talk is that in areas where we have much better age constraint, we can actually have much better high resolution Holocene records for this period of time, the last 15,000 years, which could actually inform us more than what we can get from this longer term glacial history. So that shows that the Holocene glacial records indeed can be used as an analog for future climate change because they have the ability to tell us more about glacial dynamics modulated by climate forcing. There are still many unanswered questions that I'm trying to resolve, like what the role hypsometry plays in modulating intra-regional variation in glaciers. So that are some of the points that I did not basically address here is that within each climatic region, there are still some variations, and they could be explained by changes in the hypsometry. So my larger goal is to develop a robust numeric model that basically take into account all these factors to help us better project how this glacier will behave in the future. Now, to compare and resolve whether the quaternary glaciation was synchronous across the origin or what causes their variation apart from the preservation of moraines. So basically, there are still a lot of unanswered questions. As you can see in my previous slides, that I have very good data for one region to tell us more, but I still lack data points in other areas. So I need more data points, or we need as a community more data points to resolve all these issues. Lastly, what's the role of mid-latitude westerlies plays in driving glacial advances? Now remember, I told you that most of the northern glaciers are sensitive to precipitation change. Unfortunately, most of the data points are also coming from these glaciers. So our results are biased towards the more precipitation sensitive glaciers. So we basically overinterpret sometimes that these glaciers are indeed only monsoon influenced. But our results also shows that there's a higher chance that the mid-latitude westerlies also is a big factor in driving glacial advances. Maybe not in the same extent, but they do have some importance. So if we can use more of these southern glaciers that are very useful for Holocene, then we might get much better idea about the role of mid-latitude westerlies and not just monsoon. And lastly, I would like to thank my funding agencies. These agencies funded all the field work and the logistics during the entire project and some sample cost. My collaborators, my PhD advisor, Lewis Owen, my friend Elizabeth and Orr, you might have seen her in some of the photographs, and Mark Caffey helped us mostly with the sample costs in their lab. And also University of Cincinnati provide us the geochronology lab to do all these dating measurements. And computation has been done using the Ohio supercomputing systems. So with that, I think it's a long talk and you might be exhausted, but I'm happy to explain to you things in details, happy to take questions, and thank you so much.
Thank you, Sourav. It has been a really enlightening lecture, especially for my students from graduation or post-graduation who are not exposed to the level of research that can go on. So many of the participants has been putting questions, at around 20 questions noted down. So I'll ask you some of the ones that have been repeated. Some of the participants are asking that the lockdown effect has caused a lot of positive impacts on the environment, like cleansing of rivers and the minimization of the air pollution. So do you think it will be having an effect on the glaciers as well, a positive impact on it?
So the short answer is yes and no. So the yes, because any carbon footprint is bad for these glaciers at the moment, because we're basically giving more carbon by using more of a vehicle and other things, where we're burning the fossil fuels. The more carbon dioxide and carbon monoxide and methane are in the atmosphere, it contributes to increase in temperature. So definitely, if you reduce that, it would have an impact. Now, glaciers are not impacted by just by annual variation. So I told you that there's the definition of glacier itself is that there should be a net accumulation over a period of time so that the ice body can start moving by the gravity. So whatever lockdown impact we have, it definitely would reduce some of the carbon footprint, but we might not see it more than just a small annual layer of this glacier. So if we can actually, instead of putting more carbon in the atmosphere, if we can just conserve it, if we can, like using more renewable energy and all, then over a period of 10 years, then we would definitely see a huge impact in the glaciers. At the annual time scale for a few months of lockdown may not have huge impact. It is still better because a river has much lower response time, but a glacier has, as I said several times, a few hundred years to even 1,000 years of response time, depending upon the size of the glacier. So a few months, you shouldn't expect to have huge change. But this is a good time to reevaluate our priorities.
Thank you, Sourav. There is another question from Shushmita Pai. How realistic are simulation of terrestrial carbon storage at the last glacial maximum?
So this is something is beyond my expertise, but it depends upon like the kind of studies you're talking about. Remember one thing, that all models are wrong, few are useful. So whenever you're talking about simulation of carbon storage and everything, they are inherently bad because they are based on certain assumptions, because human brains can only resolve or make estimates of certain quantities, if not all quantities. Being said that, there are many models that basically shows a promise. They helps us to understand that what we don't know and what we could not basically understand or observe in our human timescale. So in that context, they are very useful. Are they 100% accurate? nobody would say yes. Are they useful? Yes. So if your question is, you can rely on them, depending upon the study, and good studies has good citations, good impact, then yes, that means that model actually is better. They're predicting things better than the models that are not so good. In a nutshell, it really depends on the study, but they do have a very positive impact in recent research, because earth science is no more a descriptive science. It's not just a geography or geology or environmental science, it's all together, and it's very quantitative. So simulations are a great way to understand things that we cannot understand in our human time scale or with our human organ, basically. Does it answer the questions, I guess?
Yes, yes, Saurav, you are completely right. I'll just put another question because of the constraint of time. Glaciers are retreating due to climate change, but some glaciers like Pooch in Leh are advancing. Why this anomaly occurs? Is this only depending on monsoon? This question has been given by Ria Day. The rest of the other questions, I have noted them down. I'll mail it to you and maybe you can later on reply to it.
Sure, sure. Yeah, it's a really good question. I think the answer is I do not know. I know about the glaciers. I know Pooch glaciers. I know that some of these glaciers are advancing, including some in Karakoram, which I just showed. Some of them are surge, so they're a little bit different because surge generally happens is a higher glacial advance in a very short period of time. And that probably has nothing to do with the mass balance. But many glaciers are not surging, but they're still either stagnant or advancing. In a smaller catchment scale, where the question is coming, we still do not know the impact of microclimate, the impact of hypsometry that I mentioned several times, that hypsometry can play a huge role. One side of the range, you can see the glaciers are retreating faster, and on the other side of the range, you don't see any changes or even advance. So I think the future research is more about understanding this variability. Right now, many of the projects, many of the papers that came out looked more about the recent changes based on the satellite images, and they talked about these variable changes. I think we as a glaciologist or glacial geologist need to go into those areas, not only need to do a catchment specific high resolution studies, but also look into the overall picture in the entire region to get a better understanding. So I don't have an answer for you right now, but that's definitely something that many people are working and trying to understand. And hopefully, if somebody is interested and has a very good project in mind, you can contact me via my email, and I would be happy to write proposals, and we can basically start a project. So yeah, just feel free to contact me and see if we can figure that out. But I don't have an answer for that particular glacier.
Thank you, Sourav. We have participants from all across India, starting from Jammu University, Kashmir, Delhi University, in parts of Guwahati, and even from University of Madras. So we have huge, around 1,000 participants. Some are watching them on YouTube. And thanks a lot for such valuable presentation. I think many of my students will be very much inquisitive and really they would love to work on this, and will definitely get in touch with you to know more. And thanks a lot. And I would request the participants to even log into get into the YouTube channel, because we will be giving you some short MCQ related questions and some short questions which if you go through Saurav's lecture, I think you'll definitely be able to answer. 40% is the cutoff marks to get a certificate. Sorry for being mean, but this is in order to have a proper education system, there should be no forgery. So that's why. And thank you, Sourav. And I would like to tell all the participants that because of copyright issues, the lecture by Manishika ma'am has already started in a YouTube link, which I am sharing right now on my screen. Just kindly check it. This is the YouTube link. I hope everyone can see my screen. So please log into this YouTube link. I have been also posting it in the chat box to get in touch with her. Thank you. Thanks a lot. Thanks again, Sourav.
Thank you. Thank you for having me.
Ma'am,
Good
second
to see
session
you all.
Ma'am, when
Yeah.
our second session is start?
Yeah, the second session by Dr. Deblina Majumdar would be starting around 4:30. I think it's late night sort of at your place. Thanks for your, efforts. And in case of even Debolina, it will be around 5:36 in the morning. She will wake up for you all to deliver her lecture. So Vish will join again after the lunch session. Thank you. Thank you so much.
Yeah.
Thanks, Saurav.
Thank you. Thank you, everyone.
Thank you, Sourav sir.
Thank you. Bye-bye.
Bye. Bye.
Bye bye.